This meeting is being recorded.
So now we're going to look at another addition. So we're going to add now in section 810 halogens, right? So in this scenario here, we have diatomic chlorine that is added across our double bond, and this is our product here, right? So we add two halogen atoms in this mechanistic approach here, in this halogenation. So let's take a look here. There's one specific production of polyvinyl chloride that is pointed out down here. So anything that is kind of a special case or pointed out specifically in the slides, take note too, because you might see something like this on a quiz or exam later on. So there we have the process from our ethylene starting material, forming our vinyl chloride, and then our final polymer product. So halogenation will only find practical use for Cl2 and Br2. I2, we just get a poor yield, very low product formation, and then diatomic fluorine is just very energetic, very violent process, they call it. So we're going to look at halogenation specifically with diatomic chlorine, diatomic bromine. Notice that we have a stereoselectivity here of anti-addition. So our pi bond, we see one addition in a wedge here, one in a dash, and then vice versa, one on a dash, one on a wedge here. So we're going to end up with anti-addition. So Br2, we know it's a nonpolar, right? Because it's the same atom bonded to the same atom. Therefore, they have equal electronegativity values. So we will call this a nonpolar covalent bond. But nonetheless, we can polarize a nonpolar bond. So we can induce a dipole, right? We can create a dipole. So our alkene, right, our double bond, our pi bond, will act as the nucleophile. It will distort, right, the electron cloud on this bromine here. And this bromine will become slightly positive, right? So this one over here near the nucleophile. And then the electrons will then be passed on to this bromine. So what will happen is we will add one bromine on this end, create a carbocation on this side here, and the other bromine that has inherited those electrons involved in the bond has now become a bromide ion. And then that will continue in the next phase here, the next step, to add. Hold on, let's see here. So that would add onto this spot here, right, with the second addition. So when we have a cyclic structure like this here, we're going to see that syn addition just doesn't occur, right, in this specific example. Well, I'm sorry, in any of the halogenation mechanisms, syn addition doesn't occur, mainly because of, this bromine is already here. It's just a lot more accessible for the bromine to attack down here at this cationic site, right, due to steric hindrance again. And this we can see the breakdown, right? So we form, similar to the mercurinium ion, we form this bromonium ion, and that is why, right, the partial positive charge that's passed down to either of these sites here would be on the other plane or the other surface where the double bond was. So one bromine has added and forms this bromonium ion, and then the other bromine adds to the other side. So we can see this attack kind of outlined here, right? The bromine attack in this SN2 process ends up giving an anti-addition, and of course we would also have the enantiomer. So there's also halogenation in non-cyclic structures, right? So we have stereospecific products that would result. So if we have a cis butene in this example here, we'll see anti-bromination, right? But when we have a trans to butene in this example here, we create a meso compound, and right, this is an alkane now, so we can have free bond rotation. And if we flip this bromine up, we would end up with only this product here. So again, depending on what you start with, you're going to end up with a specific product. So that's called stereospecific reactions. So very similar to this bromination or halogenation is halohydrin formation. So this is when we have like Br2 or Cl2 and water reacting, and we'll end up with a similar anti addition here, where we add our halogen on the one plane, right? We have the similar bromonium ion, or with chlorine as our reactant, the same process occurs, and our hydroxyl group would add to the other plane, the other side. And just like with the bromine, right, we'll end up with the enantiomer. With the chlorine, this halohydrin formation, we also get the chlorine enantiomer. And just for fun, this is called a chlorohydrin. So again, we talked about stereoselectivity. Regioselectivity is also a factor here. The halogen tends to add to the less substituted carbon, right? So over here is where our halogen is added, over here. And then the OH, the hydrogen portion, right, adds to the more substituted carbon. So we have stereoselectivity to think about, regioselectivity to think about as well. And this walks us through kind of the why, right? Why the H2O is faster when it attacks the less substituted one, why we see this regioselectivity. But you do not need to memorize all the steps in the mechanistic breakdown here. But we do need to be able to predict, right, our final products. So that brings us to the end, right, of this section 810 on halohydrin formation. And previously we looked at halogenation in section 810. So next time we'll pick up with 8.11.